Today's video deals with something that's referred to as enthalpies of formation. When an enthalpy change happens in a chemical reaction, sometimes they will give you some additional information about the type of reaction that's happened. And again, that's not to mess with you, it is actually to help you a little bit. So sometimes you'll see things like this where it says delta H and then COMB, where basically all that they're saying is that's the enthalpy change that happens when this combustion reaction happens. Or sometimes delta H with a VAP afterwards refers to when something vaporizes, something converts from a liquid to a gas. So enthalpy reactions can come in lots of different ways, and so can enthalpies. There can be enthalpies of combustion, enthalpies of vaporization, enthalpy of fusion, which is when something melts. And don't worry about what all those different enthalpies are, just know that they all refer to the change in the enthalpy in that chemical reaction. Okay, so another type of enthalpy that we need to be familiar with, these are just different types of actual chemical reactions: combustion, vaporization, fusion, whatever it happens to be. Okay, another type of reaction that can happen is what's called a formation reaction, and you can have an enthalpy of formation. Okay, a formation reaction is a reaction where something is formed from its elements, so things that are in its elemental form combining together to form a new substance. Okay, if something is already in its elemental form, and remember Brinkelhoff, because that's where people mess this up, those, anytime they're by themselves, their elemental form isn't Br or I, it's Br2, it's I2, etc. So whenever a substance is in its elemental form, then it has an enthalpy of formation of 0, because how much energy is released or formed when something's already in its elemental form? That's just how it is. There is no enthalpy of formation for something that's in its elemental form. So it has an enthalpy of formation of 0. So what does this look like? Well, example 1 says write the equation that would represent the enthalpy of formation of CO2 that releases 393.5 kilojoules per mole of reaction of heat. Okay, so we have to form CO2 from its elements. So what does that mean? It means you write C, and again, really all you're thinking about here is which ones are the diatomic molecules. Okay, carbon is not, so we can just write C plus O2, because that's the elemental form of oxygen, produces CO2, and the enthalpy change for that reaction, since it releases 393, is negative 393.5 kilojoules per mole of reaction. Okay? And that's what all of enthalpies of formation, that's what they look like, is you have to write things forming from their elements. So even something like Na3PO4, what would be the enthalpy of formation of that one is you would have 3 sodium atoms plus a phosphorus atom plus, and remember O is always O2 just like here, so it'd be plus 2 O2s makes Na3PO4. Okay, the only time it gets tricky is when they give you a problem like here on example 3. We'll go back to number 2 in just a second. Okay, it says write the equation to represent the enthalpy of formation of 1 mole of NaNO3, which means you can't have more than a 1 in front of the NaNO3. So we're going to form NaNO3, and again, the enthalpy of formation. And again, I could have written that up here as well on this example, delta H with the little F there. And again, that means enthalpy of formation. Okay, it's going to equal, and again, whatever, they don't give us the number, so it doesn't matter. Okay, but we have to form just 1 mole, which means we cannot change the number in front of here. So, well, okay, so we're going to have Na, that's no problem. But then we have nitrogen, and nitrogen is a diatomic molecule, but we can only have 1 atom of nitrogen. So we have to write it as N2, but how can we have N2 just be 1 nitrogen atom? Well, we would have to write 1/2 of an N2, and that's exactly how you would do that. Okay, and then the same thing with the oxygen. We need 3 oxygen atoms, but oxygen's O2, so what would you have to put in front of it? 3/2 of an O2. Okay, and that's exactly how you would write that. So if it says 1 mole of something, it means you can't change that number right here. Normally, you would double that, and then everything comes out to be whole numbers. But this is one of the times where absolutely you're going to see fractions in a balanced equation because, again, we can only have 1 mole, not the 2 moles that I had written there. Okay? All right, now, enthalpies of formation. Who cares about them? Why do we need to know about them? Because you can use them to find the enthalpy change for a completely different reaction. Okay, so far we've learned 2 different ways about how to find the enthalpy change for a reaction. You can use Q equals mc delta T, and you can find the Q value. Once you know the Q value, you divide by the moles of whatever that substance is, and then you decide, is it positive, is it negative, is it exothermic or endothermic? Okay, and then we learned that you can take the bond, how much energy does it take to break the bonds of the reactants? How much energy is released? Remember, it's always negative, the bond energy of the products, because you're creating bonds, and that always releases energy. You can use those 2, put them together to find the enthalpy change for a reaction. Okay, our third way of finding the enthalpy change of an overall reaction is to take the sum of, that's what that means right there, the sum of the enthalpy of formation of the products minus, just like this one up here, minus the enthalpy of formation of the reactants. Do notice here, this is really, really important. The only time it's ever going to be bond energy of reactants minus products is when you're using bond energies. When they're saying the energy of this bond is this much, the energy of this bond is this much. We're actually going to learn a couple more equations, and every single time it's going to be products minus reactants. Okay? With bond energies, it's not, though. It's reactants minus products. That's really, really an important distinction that you need to remember there. Okay? So, well, what does that mean? Well, let's look at this example right here. Calculate the enthalpy change for the reaction that occurs when propane, C3H8, okay, so let's go ahead and start writing this balanced equation, burns in air. So when something burns in air, what is it reacting with? Oxygen. Producing, so that's our arrow, carbon dioxide, so CO2, and water, H2O. Okay, so we need to write a balance. We need to balance this. We've written the equation. Now we need to balance it. So we're going to put a 3 there, 8 hydrogens, so we need a 4 there, and that makes 3 times 2 plus another 4 is 10, so we need 5 oxygens there. Okay, and so now that equation is balanced. Now they want us to, now it says calculate the enthalpy change for the reaction. So they're asking for this. Okay, so the enthalpy change for the reaction is going to equal the sum of the enthalpies of formation of the products. So here are our products. So we need to know, what is the enthalpy of formation of CO2? Well, we just used that up here. It's negative 393.5. Now, that's for one CO2. How many CO2s do we have? Obviously, we have 3 of them. So we're going to go 3 times negative 393.5 plus, because remember, it's the sum of, and then our other product is H2O. And here they tell us the enthalpy of formation of water is 285.8 kilojoules, again, per mole. That's per 1 mole of water. But again, we have 4 moles, so I'm going to put a 4 there. And then negative 285.8. And that's my products. So remember, the sum of the enthalpies of formation of the products minus, and then now the sum of the enthalpy of formation of the reactants. So one of the reactants is oxygen, and notice right away, why is the enthalpy of formation of oxygen gas not given in this problem? Because oxygen is in its elemental form. And remember, things that are in their elemental form have an enthalpy of formation of 0. Okay, so what do we do with this? In terms of the math in our equation, nothing, because it's in its elemental form. Okay, and then we just need the enthalpy of formation of propane, which they tell us is negative 104.7. Again, be real careful with the negatives here. 104.7. Again, there's only one of them, so we're just going to put, that's all we put for our reactants there. Okay, so at this point, go ahead and pause the video, do the math yourself, check to see if your answer comes out to be the same as mine. And who knows, I might be wrong. Okay, so I'm going to go 3 times negative 393.5 plus 4 times negative 285.8. And then I've got a double negative here. I'm subtracting a negative number, which for in terms of ease, that just means I'm going to add. So I'm going to hit plus 104.7. And then I get my final answer of the delta H for the combustion of propane is negative 2,219 kilojoules per mole. Okay? So that means that for every mole, and think about this, like this is the reaction that happens inside your barbecue if you have a propane tank. Okay, for every 44 grams of propane that you use, that's a mole, right? Propane has a molar mass of 44. Every 44 grams of propane that you use, which is about 1/10 of a pound. Okay, for every 1/10 of a pound of propane that you use, you release about 2,219 kilojoules of heat, that's a good amount of heat. Okay, and that's why propane works really well with ovens and barbecues and cooktops, things like that, because the amount of energy that gets released is really, really big. Okay, now remember, another way that we could have calculated this without using enthalpies of formation is they could have given us the bond energies for all of these, okay? And again, I just want to just remember that we could calculate how many bonds are breaking in C3H8, how many bonds are breaking here, and that would be our endothermic part. And then we would do the same thing. How much energy is released when those carbon-oxygen bonds are formed here? How much energy is released when those HO bonds are formed? And guess what, guys? You know what you get as the answer when you do it that way? You get negative 2,219 kilojoules per mole. Again, assuming I did my math correctly, and it actually is negative 2,219. Okay, so that's enthalpies of formation. So enthalpies of formation, again, is when you form something from its elements. Okay, and typically it's going to be it's an exothermic process because it basically is a synthesis reaction. You're really not breaking bonds, even though in this case, even right here, you've got to break that bond between oxygen. Typically, and that's why I say typically, it is an exothermic process because most of the time it is just a synthesis reaction. Okay, and then you can use those enthalpies of formation, which again, this equation here is given on the equation sheet. This equation here, though, the bond energy of the reactants minus the product, this one is not given on the equation sheet. That one you just need to know that, okay, it takes energy to break bonds. It releases energy when bonds are formed. And so you have to use that negative there in the middle. But this one they will give you on the AP test, okay? And then sometimes, yes, you will end up with fractions when you have to create just 1 mole of a product. Okay, and that's enthalpies of formation.